All right, let's continue. We were trying to find a graph for f of x is equal to x divided by the square root of x squared plus 2. All we've done so far, and it's taken like 13 minutes, found the domain, found the intercept, singular, and our end behavior turned out to be two horizontal asymptotes, which our graph does not cross. Okay, it looks like it's possible that this graph has some sort of symmetry. So let's check to see if it does. It's very simple to see if a graph has symmetry. You just plug in negative for your x. So symmetry. Question mark. All right, so I'm going to take negative x, plug it in for x, and see what happens. If I stick in a negative for my x over the square root of negative x quantity squared plus 2, the negative up top stays, but on the bottom, I'm squaring that negative, and it's going to go away. And I can see that this is exactly equal to negative f of x. What does that mean? This means that it's odd. It's an odd graph. It's going to look sort of like this. It has rotational symmetry around the origin. And, maybe that's something that I could kind of expect by looking at a graph that looks sort of like, maybe something like that, right? Okay, so now it's time to start some calculus. All of that is the process is gonna start with finding some critical numbers. Critical numbers happen where your first derivative is equal to 0. So let me write my function down one more time. I've got x over x squared plus 2. I'm gonna write that to the 1/2 power, and I'm gonna have to use the quotient rule on it. Hooray! So f prime is equal to, derivative of the top is 1 times the bottom, x squared plus 2, 1/2, minus the first one times the derivative of the second, leapfrog the 1/2 down, x squared plus 2 to the negative 1/2, and then times 2x for the chain rule part of it, all over the denominator squared. Denominator squared is just going to leave us with x squared plus 2. Square and the square root cancel each other out, of course. All right. Now then, let's cancel this and that, and then maybe rewrite a little bit and then do a little bit of fancy factoring, because it's really going to help us figure out what our critical numbers are, and also set up intervals to do testing for increasing and decreasing. So x squared plus 2 to the positive 1/2, this x and this x will multiply together to give us a negative x squared plus 2 to the negative 1/2 power, and then bring that denominator down. All right, the common factor that they both have is some factor of x squared plus 2, and remember you always take it to the lower exponent. In this case, it's going to be to the negative 1/2 power. So x squared plus 2 to the negative 1/2 power, boop, boop, boop. And then I want to divide both of these things by x squared plus 2 to the negative 1/2 power. So these have the exact same base. All I want to do then is subtract the exponents. It's 1/2 minus a negative 1/2, which means it's 1. It's x squared plus 2 to the first power. I'll do that right over here. It's like a to the positive 1/2 divided by a to the negative 1/2 is equal to a to the positive 1, right? Whenever you subtract those exponents. And then finally minus x squared, because of that is the same thing as what we factored out, over x squared plus 2. Cancel, cancel. How convenient was that? So convenient. All right, and then I'm going to bring this negative exponent down here to the bottom. So it is to the negative 1/2. It'll be to the positive 1/2 whenever I bring it down to the bottom. And then think about this. I have a to the positive 1/2 times a to the 1 power. I'm going to add those exponents, and this is the same thing as 2/2, which is going to give me a to the 3. That's a 3. Take my word for it, 3/2. Which means that our first derivative finally is 2 over x squared plus 2 to the 3/2 power. All right, what about critical numbers then? So the critical numbers happen where this derivative is either equal to 0 or it's undefined. Well, since the top is 2, it's never equal to 0. And since the bottom is the same exact kind of square root that we talked about before, which is also never 0, you have no critical values. None. What's that mean? This means that there are no relative extrema. No relative extrema. There's no relative mins and maxes. This graph is either always increasing or always decreasing. There's words for that. What is it called? Strictly monotonic. So let's see. Which one is it going to be? Well, this down here in the bottom, I'm taking the square root of this thing. Doesn't even matter. This is always going to be positive. 2 is always positive, which means that f prime of x is greater than 0 for all, I'll just do this, for all real numbers. This means that our function is always increasing. Always increase. Oh my gosh, I'm having such trouble. Always increasing. There we go. All right, so that's a handy piece of information to know. We have no relative extrema, and our function is always increasing. Let's go back to the sketch of the graph here. So kind of would make sense that we're doing something like this, that our function is always increasing. Okay, so then there is one more piece of calculus to do on this, and that is adding an extra page so we can find the second derivative. Not to do the second derivative test, because now second derivative test does the same thing that the first derivative test does, and that is it tests for relative extrema, which we already determined it has none. But we might want to know what its concavity is and possible points of inflection. So for that, we need the second derivative. So what I am going to ask for you to do, given f of x is equal to 2 over x squared plus 2 to the 3/2 power, is to find the second derivative. Go ahead, pause the video, pause it right now, find your second derivative, then unpause it, and see if you get the same thing that I got. All right, are you done? Let's see what it is that you got. So I'm going to avoid the quotient rule by rewriting this as 2 times x squared plus 2 to the negative 3/2 power. No quotient rule necessary. And now the second derivative, leapfrog that 3/2 down, that half and the 2 will cancel out, giving me a negative 3. X squared plus 2. Subtract 1 from this exponent, that's going to make it a negative 5/2. And then multiply this times the derivative of the interior, a 2x. All right, and now let's clean this thing up just a little bit. The negative 3 and the 2x are going to stay up top to make a negative 6x. And then on the bottom, we will bring that 5/2 power down to make it positive, x squared plus 2 to the 5/2 power. All right, so now we want to find its supercritical numbers. Supercritical numbers. That happens where the second derivative is either equal to 0 or undefined. Well, it's not undefined, because again, we have this square root that's down here on the bottom, but it is entirely possible that it's equal to 0, right? Because we have negative 6x is equal to 0, and that's going to equal 0 whenever x is equal to 0. X equals 0. What could possibly happen here? This could be a possible point of inflection. How do I know? What I'm going to do is a test for concavity. So the test for concavity looks sort of like the first derivative test, except for you're doing it on the second derivative, and we need some intervals. So the intervals taking the domain of all real numbers and just breaking it up at its supercrit. So from negative infinity to 0, and then from 0 to infinity. We need to pick a test value. How about positive and negative 1? Where do those go? They go into the second derivative if we're testing for concavity. Okay, so if I plug in a negative, let's see, it's coming back over here. If I stuck a negative, notice that the bottom is always positive, so we don't have to worry about it. So if I stuck in a negative, negative out here times a negative in here is going to make this thing positive, meaning that f of x must be a cup, concave up. All right, and if I stuck in a positive 1, that's going to be a negative times a positive. This whole thing is negative. Means that it is concave down. It's a CD, concave down. What did we just find here? We have a point of inflection. Now, ordinarily, I would have to take this x value of 0, plug it into the function to find the y value, but we've already done that because it just happens to be 0, 0 at 0, 0. If I were going to justify this, if I had to justify it on any kind of AP exam, I would say since f double prime changes signs at x is equal to 0. Okay, I think that we have enough information to put all of this together. It's always increasing, strictly monotonic. On the left side of 0, it's supposed to be concave up. And on the right-hand side, it's supposed to be concave down. This is a point of inflection, and we are sandwiched in between these two horizontal asymptotes. This is going to look very, very similar to boop and boop. It's going to look very similar to the arctangent graph. All right, I'm going to come back over here to, let's see. Let's look at the perfect graph of this thing, which should be right around here. And let's see how perfect we got our graph. There's our horizontal asymptotes. There it is. Fantastic. Man, if you were to put this thing side by side with the one that we just did, it would be pretty close. All right, there you go. You've got a complete graph for f of x is equal to x divided by x squared plus 2.